Okay, let's go ahead and get started today. We're just going to kind of do essentially a review of thermochemistry because it's probably a good idea to do some more practice problems, right? So let's go ahead and do that. So with this, we're going to kind of just do some random homework problems, ones that you aren't assigned but are still going to be kind of useful for us. So this will be just kind of a thermochemistry review. Okay, so with this, let's go ahead and let me just grab your homework here. We'll do some problems. Okay, so let's start at the beginning here. Alrighty, so let's go ahead and do some of these things. Let's start with number 42. Let's start with that. Let's just kind of do a general conceptual review. And so with this, if we look at it, we're going to start with predicting the delta S for the system. If we're given a couple of conditions. So one of them is molten gold solidifying. So that means we're going to be starting off with liquid gold turning into solid gold. And so if we're trying to predict the change in entropy here, yeah, we're expecting this one to be negative. Because we're going to be reducing the degrees of freedom that these are allowed to use, right? So we're basically taking away the rotation ability from the molecules as we solidify. So we're going to be reducing the entropy there. As a result, it's going to be negative. All right, so gaseous Cl2 is going to dissociate to form chlorine atoms. And so we're kind of just looking here now to just have a look at moles of gas, right? So we're going from 1 mole of gas to 2 moles of gas. That's always going to make things more entropic, so we're going to have a positive value there, absolutely. All right, the next one is we have gaseous carbon monoxide plus gaseous hydrogen to form methanol in the liquid state. And so with this one, we're going to need to balance this, I suppose. We're going to see here again, we're going to have 3 moles of gas on the left, we're going to have 0 moles on the right. So chances are this is most likely going to be negative. That being said, we do have some benefit here to making a more complex molecule because that's going to give us kind of more things to do. Remember that entropy does increase with molar mass. So, but because we're having 3 moles of gas turn into 1, probably that's going to outweigh the any kind of benefit from making a more complex molecule. All right, and the last one here is going to be precipitating calcium phosphate. So we're making calcium nitrate here plus ammonium phosphate. All right, and with that, we're going to get calcium phosphate, and what is it, ammonium nitrate. Okay, so with this one, we have aqueous, solid, aqueous, right? Precipitation reaction. If we were to balance this, we would see 3, 2, and 6 would be our coefficients here. If we want to think about what's happening here, we're going to see that we have a whole bunch of ions that's kind of floating around in solution, And essentially we're just removing some of the ions from the system. In doing so, that is going to end up lowering our entropy, right? We're forming a solid that can no longer move around. So in solution, things can translate, they can rotate, vibrate. We're making a solid, we're removing ions from the solution. And so as a result, we're going to end up with a lower entropy overall for our system here. And so that's going to end up being entropically unfavorable. We'll probably remember also like making solutions, dissolving solids is entropically favorable, so perhaps that makes a little bit of sense there. Alrighty, let's see. How about now, or any questions on that before we do some more? Alrighty. So 52, let's go ahead and do that. So this one is wanting us to calculate delta S as well as kind of explaining it. So if we look at A, we're going to have hydrogen nitride plus ammonia turning into ammonium nitrate. Before we calculate it, we should probably just predict it. With this one, we would probably predict it should be negative. Because we're going with 2 moles of gas, we're making a solid, so we're definitely reducing our freedom there. And so we're going to want to go ahead and calculate that. So if we do that, we're going to have our products minus our reactants. Looks like things are going to already be balanced here, so we don't have to worry about that. And so we're going to go ahead and pop open our thermochemical constants page. Where did it go? Here it is. Alright, so with this, let's go ahead and look these up. These are all nitrogen-containing compounds, so let's go ahead and check that out. So we have ammonia gas has an S of 192.5. We have HNO3 gas is 266.4. And then the ammonium nitrate solid is 151. And so doing this, of course, we can already see it's going to be negative. I'll let Kevin actually do the calculation, though, because I'm too lazy. But we're going to see it's going to end up being negative, right, as a result. Okay, awesome. We even got someone else calculating for us. Kevin's been replaced, rather. So there's probably a mole in here also somewhere. Awesome. So we predicted it would be negative because we're reducing the amount of gas. We're making solids out of it, so we were able to get that out. Awesome. Let's do, let's just go ahead and do C, I suppose. We have calcium carbonate as calcite. Plus 2 hydrogen chlorides turns into calcium chloride plus carbon dioxide plus liquid water. So with this one, what do we kind of think is going to happen here? Let me put the creature outside 1 sec while you guys think about that. Come here, creep. Okay, come on, buddy. Get out of here, mister. Okay. With this one, it may not be as obvious to us, but there's kind of a couple things we're going to look at here. We are going to end up having 2 gas molecules going to 1, but we are producing different molecules. So this may be, not as obvious to us right away. Um, so let's see what happens. So if we go ahead and do this, let's look up the, I guess, calcium first. So if you look up calcite, it has an S, or I guess we should set this up, right? So delta S is going to equal the calcium chloride plus the carbon dioxide plus the water minus 2 times the S of HCl minus the S for calcite. So calcite looks like is 92.9. We have what other calcium things over here? CaCl2, 104.6. Carbon dioxide, it looks like we have 213.6. Let's see, we need chlorine. So HCl gas is 186.7. And then water. That's going to be under oxygen, I assume. Yes, there it is. And this is liquid water, so it's 69.9. Yeah, so this is interesting. It's going to be a close one, right? So we'll see. So I mean, we have, that's the idea here is we have now kind of conflicting things. We have fewer gas molecules, but we do have more complex molecules on the right, and we still have a liquid and a gas. I mean, we'll see. So, doing all this fun stuff, what are we going to end up with? Eyeballing it looks like it's going to be pretty close to neutral, but let's see. So we get negative, okay. So it is slightly entropically unfavorable, it looks like, at the end of the day. So, but obviously we can see the magnitude of this is not as severe as the last one was, where we had very clearly two gases turning into a solid. That was strongly entropically unfavorable. This one is kind of minorly unfavorable, entropically speaking. All right, so in this case, the gases have won out here. Alrighty, let's see. How about we do... Let's do, how about 56? So this one says a certain reaction has a delta H of 23.7 kilojoules per mole, or just kilojoules, I suppose, and a delta S of 52.4 joules per Kelvin, both of these being positive quantities. First one's asking us if it's exo or endothermic. Hopefully we can tell right away this is going to be endothermic, right? Because we have a positive delta H. And if we look at part B, it's asking us, do we have an increase or decrease in the randomness or disorder? So that's, of course, asking about entropy. This one is a positive, so we're looking for an increase in disorder. That's going to be part B. And part C asks us to calculate delta G. And so we remember that delta G is going to be delta H minus T delta S. And I think this one said 25 degrees. Yeah. So that'll be 298 Kelvin. And so that's going to be 23,700. Remember, we're going to want to have everything in the kind of correct units here. So we should put them all in joules per mole or kilojoules per mole, either way. But we'll want to, I'm just going to put it in joules for now, so we'll see what we get. Minus 298 times 52.4. Let's make that a little bit more obvious. Okay, yeah, I would expect the same thing here. So we're looking at the temperature is going to be a factor here, since they're both positive. All right, and so if we go ahead and calculate this, we get... Yeah, so it's going to be positive at this particular temperature, but it may be negative at a higher temperature. All right, we have a slight discrepancy here. So let's go ahead and I'll do the calculation. So 23,700 minus 298 times 52.4. 52.4, sorry. And so, yeah, I got 8.08 here. Kilojoules. It's positive. So, but Kevin is right also. At higher temperatures, the entropy term would be kind of more, it will take over and it'll eventually make it negative at high enough temperatures. So you're both definitely right on this one. So, but the calculation, yeah, should be 8.08. So sorry about the messy writing there. We do actually have a term for this. I suppose we haven't said it out loud, but this sort of reaction is something we would call endergonic. Endergonic means it has a positive delta G. The opposite is exergonic for a negative delta G. Let's see. In the last part of this one, is this going to be spontaneous under standard conditions? So this would not be spontaneous, right? Because it's a positive delta G. It's endergonic, not spontaneous. At least in the direction that it's given. All right. Any questions on that one? It's nice to have like discussion here. Okay, let's see. What else shall we do? All right, let's do 61. If there are any in particular that leap out at you, I'm happy to go over those as well. I'm kind of just choosing kind of a selection of problems just as I look through them. So if there's any that you say, hey, I was looking at, 58 and I'm not sure how to do it or whatever, I'm happy to do that. Yeah, we can do 23. Yeah, for sure. Okay, so let's do that after this one. Alrighty, so this one says octane is going to be burned to provide CO2 and water. And so we're going to want to predict whether this is going to be more negative or less negative than delta H, the delta G. So without actually calculating it. So we're taking C8H18 liquid plus some amount of oxygen, turning it into carbon dioxide plus water. Actually, I think this one has us producing liquid water, yeah. So we're technically going to have to balance this. Let's hope it works out nicely. Let's see, if we go ahead and put 8 here, we're going to have, let's see, we have 18 waters to deal with, so that'll be 9 there. We have 9 oxygens plus 16 oxygens. That is 9 plus 16 is 25, so 25 over 2 would be our coefficient there. If we make everything nice, hoping my balancing works out here. Trying to do things in my head, of course, always goes wrong. But let's go ahead and see here. So with that, let's try and predict what's going to happen here. So it's asking us to predict more negative than delta H for this one. So that question is essentially therefore asking us what's happening with entropy, right? Because we know delta G equals delta H minus T delta S. So if we're looking at that, of course, temperature has to be positive. So we're looking at if the entropy is going to be positive or negative, right? If delta S is positive, then yes. But if it's negative, then it would be no, right? So we'll have to make that determination. So that's kind of what we're looking at here. So we're just evaluating this equation without calculating anything, just to try and predict if this is going to be the case. And so we have some factors to think about. But so far in our other exercises, we are seeing that the gases tend to win out here. If we look here, we have 16 gas moles. And here we have 25 moles of gas. But we also just have kind of overall moles increasing in general for the water side. But we also have a very complex molecule with the octane here. So may or may not be so obvious to us. I would potentially suggest that this one might be the second case where we have a negative delta S. And we could actually calculate this if we want. We can just check for our own curiosity. I would probably suggest that it's going to be this one down here. I agree that it probably would end up being less negative because we are significantly reducing our moles of gas. But let's calculate it. Let's see. So let's just check our answer, as it were. Even though it tells us not to do that. We're just predicting, right? But let's see if our prediction is correct. And so it's a kind of a discussion, right? So we have 16 plus 18 times the S for water minus the S for octane. Oops, C8H18 minus the S, I guess 2 for that, and then 25 times the S for oxygen. Do we even have octane on our list? That's the real question. We might have to look it up elsewhere for our purposes here. Okay, let's look it up. Octane, standard entropy. Okay, so it looks like the standard entropy for octane okay, here's octane. Standard entropy of the liquid is going to, looks like to be about 360. So just looking this up. So we're just calculating it for fun. So for the octane, it looks like it's about 360 or so. So the rest of them should be on here though. So for carbon dioxide, we have 213.6. For liquid water, where is oxygen? Liquid water again was 69.9. We had 2 times the 360, and then 25 times the oxygen, which was 205. So if we go ahead and do this, it does look like it's going to be positive just from, actually maybe not. Well, let's see. I'm bad at the mental math. 16 times 213.6 plus 18 times 69.9 minus 720 minus 25 times 205. And we end up getting a negative delta H here, or delta S. So we get negative 1,169. So indeed, it does look like the gases have won out yet again. So it does seem that the gas one is the more important of the entropically determinant component here. So indeed, delta G will be positive, more positive than delta H. So if we were making gaseous water, though, it probably would switch the other way around. So, but it's because it's liquid water at this particular temperature that's causing that. Okay, so let's go ahead. 23, I think, was asked. Let's see where it would be 23 in this. 23. Okay. Any questions on that one, by the way? Okay. So reading this question, it says the normal boiling point of bromine is 58.8 and its molar enthalpy is 29.6. When it boils, is its entropy increasing or decreasing? And then after that, we're calculating the value of delta S. Okay, so with this one, 99, okay, we can do that after, sure. So A is asking us, does the entropy increase or decrease? So we're going from Br2 liquid to Br2 gas. Hopefully all of us can tell this is definitely going to be a positive delta S. Because we are definitely going from liquid to gas, so we're definitely going to be increasing our entropy over the course of this reaction. So hopefully that part's not bad. If we look at B, we're going to be wanting to remember way back a few days ago, I suppose, where we saw that we could calculate delta S by looking at the heat of vaporization at the temperature. This is going to be because we can assume that at the equilibrium of vaporizing that we are going to have a reversible reaction, which makes this possible for us. Remember that for this sort of thing, for fusion or vaporization, delta G is 0, because these are going to be kind of standard conditions for both of the things. We're going to have the bromine gas and the bromine liquid. They're both going to be kind of at their standard states. So we say delta G equals 0. And so we're saying essentially that delta S, or rather T delta S, my gosh, delta G equals 0, but delta G equals delta H minus T delta S. So delta S therefore will equal delta H over T if delta G equals 0. And so we can go ahead and calculate that. And so it looks like we've got the value here, is going to be 29.6, or let's just go ahead and make it into joules, rather. That's the trick here, right? And then the temperature is 58.8, so we're going to have to convert that to Kelvin. 59133. Okay. And hopefully we have an answer here, because I don't want to do the math. Awesome. So we do indeed get a positive number, which is always a good idea. So we end up with 89.21. Awesome. So Kevin wants to actually do a homework problem, huh? All right. Very well. Okay, so let's see. Oxidation of glucose produces carbon dioxide and water. In contrast, anaerobic decomposition produces ethanol and carbon dioxide. Using data in Appendix C, compare the equilibrium constants for the following reactions, and then we are going to compare the maximum work that can be obtained from these processes under standard conditions. Okay, we have a lot to deal with here. So if we look at these, let's go ahead and, let's kind of, I guess, write out these equations. So we've got glucose aerobically combusting, turning into 6 CO2 plus 6 waters. So let's go ahead and let's do part A first. If we look at part A, it's asking us to compare the equilibrium constants. So we're just kind of looking, which one's going to be bigger, which one's going to be smaller. So we'll be able to do that using delta G. If you remember that standard delta G is equal to the negative RT ln K. R and T are going to be constant here. So we're going to see that the bigger the K is, the smaller the delta G is, right? So small or more negative delta G would be a bigger equilibrium constant because there's a negative there. So with that in mind, we can calculate delta G for these two reactions and compare them. So let's go ahead and bust open our handy dandy thermodynamics sheet. So, oh my gosh, we're going to have to calculate delta G, or delta H and delta S for this. Wait, no, actually we have delta G's in the end of the book, so we can do that. So delta G for this reaction will be delta G for 6 times delta G for CO2 plus 6 times delta G. The 6's and the G's are just going to confuse me. For liquid water, minus 6 times delta G for oxygen, which is 0, minus 6, or minus just delta G for glucose. So remember, this is just 0 because that one's going to be in standard conditions. Okay, so we're looking at water liquid. Delta G is negative 237.1. Our other two compounds are carbon-based, so let's go ahead and look up that. It looks like glucose is negative 910.4, and carbon dioxide gas is negative 394.4. So delta G is going to be 6 times negative 394.4 plus 6 times negative 237.1 plus 910.4. All of these, of course, in kilojoules per mole. Awesome, Kevin's already done it. And doing this, of course, we are expecting this to be definitely exergonic here. So negative, oh my gosh, not a tilde, negative 2878.6 kilojoules per mole. All right, and if we look at that second reaction here, C6, H12O6, is going to turn into 2 ethanols plus 2 CO2s. Okay, so we're going to go ahead and look those up as well. So glucose we already had. So delta G for this reaction is going to be the 2 times the delta G for ethanol plus 2 times the delta G for CO2 minus the delta G for glucose. Thankfully, we already have these here, so that was 910.4. CO2 was negative 237? No, 394. And then the ethanol here is 174.8. And so we can go ahead and calculate this. I'll let you guys take that for a sec. And it's negative 228. So we can see already here that this is going to be much kind of smaller. Oh, I only wrote 28. 228 kilojoules per mole. All right, and so if we want to now look at the second one, let me find the example in the book that we used. Okay, so if we want to remember what happens with work, remember that for any sort of process, we're going to have an energy change can be related to heat and work, right? So we're going to be looking at some work here. If we're going to be comparing the work to, where did this example go? So remember that work is just going to be kind of energy that's put out, right? So we remember that from way back last semester that the change in energy associated with a process is always going to be the heat of it, any heat change that happens, as well as any work that's performed by the system. So we're going to see that if we want to calculate the work for this, we're going to be essentially looking at the energy change here. So essentially, remember, we can kind of equate Q to delta H associated with this idea. So we're going to see that we're going to have this W component is going to be a factor based on the entropy. So we're looking at entropy here because we remember that way back when we talked about gas laws, we talked about work being related to pressure times the volume, right? P delta V, rather, I suppose. And so we saw that as gases expand, they do work, right? So let me find the example here from the book. I still can't find the one that I wanted to use for this. So there's Q. Where's the one with work? Aha. Okay. So remember that for work to be P delta V, if we were to plug in our ideal gas law for this, remember that pressure equals nRT over V. If we plug this in for pressure, we're going to see the work for the process is going to be nRT associated with the change in volume here. It's very exciting. I know we're going kind of crazy with the entropy here. So if we want to consider that, remember that the work for this is just going to kind of be another form of energy that we're going to be working with. So we're going to see that if we had delta S, which could be the Q for a reversible process over T, we're going to see that can also be the work for a reversible process over the temperature. It's going to be, we can still calculate the work that can be done in this same sort of idea. So it's just a different way of looking at the energy here. So definitely a kind of a more complex part of this problem that's going to force us to look at a whole bunch of stuff we've done before. And so if we now plug in our W here that we've just calculated, we see we have nRT over V and then T and V. So what we're looking at here, we're going to see that we're going to kind of cancel out our temperatures, right? Because those are going to cancel out. Is this going to be iso volumetric? This is just standard conditions. So we're going to want to, this is odd that there's not like an actual volume change given to us. So let's go ahead and assume that we're dealing with something that's, we're just going to have them be the same if we're comparing these two processes. So really we're just kind of looking at the value of delta S. Delta equals negative W max. To be honest, I don't quite remember that when I took thermochem. I mean, it makes sense because that's when work would be maximum at the peaks of your like valley thing. Oh, really? Is it? I guess I should look these things up. In that case, yeah, I guess we can. So we'll make this a little bit easier. How embarrassing. So instead of having to calculate delta S and delta H separately for this stuff, dealing with this way is probably easier. So then, yeah, Kevin does know more about me than thermodynamics. Go figure. Awesome. Let's just do that then. So in that case, we've already calculated the delta G's. So if that's going to be the opposite of the work here, I don't remember this. Go figure. Okay, awesome. Lovely. So forget all of this hard work that we've had to do with remembering gas laws and thermodynamic equations from chapter 5 and chapter 11. So let's just go ahead and be smart about it. So in that case, the delta G's that we had calculated for the first one, for the aerobic process, was, here it is, negative 2878. So kilojoules per mole. That means apparently that without having to calculate things easily, that means the work that we can make out of this is going to be the positive version of that. Awesome. And then for the anaerobic process, it was negative 228 kilojoules per mole. And for the work for that one will be just the positive of that. Cool. Easy. So there we go. Apparently I should read the book as well. Alrighty, so we've done it. Hooray! Any questions on that one without going into the crazy other stuff I was trying to bring up? Alrighty, shall we do another one? Let's see, what's a good one to do here? Alrighty. Let's go ahead and let's do some of 96 while we're up here. Yes, that should work. Okay, so if we have 96, it's asking us to calculate Kp and delta G for these processes. We have nitrogen. Oh my gosh, it's our favorite reaction of all time. And it's telling us we have these partial pressures. And then we have our ammonia. This is 1.2 atm. All right, so with this one, we have two things to calculate. We have Kp and delta G to calculate. So with this, we're going to be looking at two different things, right? So we're going to be looking at, first here, we're going to look at these partial pressures that are given to us as Q. Those are conditions for Q, right? Those gas pressures will give us Q. We're going to calculate the delta G at standard conditions, just using our stuff from the back. And from that, we're going to end up being able to get delta G at this temperature, right? So this is, we're going to get from appendix calculations, and then the Q we're going to have to calculate here ourselves. So Q for this reaction, of course, is going to be ammonia squared over nitrogen and hydrogen cubed. So that'll be 1.2 squared over 2.6 and 5.9 cubed. Awesome, thank you. 2.7 times 10 to the negative 3. All right, so from the delta G side, if we're going to calculate delta G at standard conditions, we know that hydrogen and nitrogen are not going to matter for delta G because they will just be 0. So we're really just looking at the delta G for ammonia. Because, again, remember standard conditions for elements will be 0. Okay, so we're looking at ammonia gas. Looks like negative 16.7. I can do this one in my head, maybe. Negative 33.4 kilojoules per mole. Wait, we did this yesterday. I remember calculating that one. That number is familiar. So if we want to calculate delta G then, it will be negative 334 or negative 33.4 kilojoules per mole. Actually, I guess we need to expand this as always. Plus 8.314 joules per mole Kelvin. Temperature was, what was the temperature for this reaction? Why aren't we given a temperature for this? Well, let's just go ahead and calculate these at, let's just do it at 25. So we'll say 298 Kelvin. And then we have our natural log of 2.7 times 10 to the negative 3. If we do this, fun stuff. Negative 33400 plus 8.314 times 298 times natural log of 2.7 times 10 to the negative third. We get negative 48. Oh, did I calculate this wrong, Kevin? It looks like everything I've put in has worked. I got negative 48,000 instead. Let's just double check our calculations here. You missed an 8. Okay, cool. Okay, so then presumably this one will be good there. And so that will be the delta G for this reaction at 25 degrees. This question apparently is bad for not giving us a temperature, so oh well. Because, of course, K will vary with temperature, right? So we're going to just be calculating it at one particular temperature. If we wanted to find Kp, remember that that is going to be e to the negative delta G over RT. Remembering that we got that from delta G equals negative RT ln K. So if we do this, we have our delta G was negative 33.4. I guess we need to expand that, sorry. And then we're going to have 8.314, and then the temperature 298. We do this. I feel like we did this exact one yesterday, actually. E to the negative 33,400 divided by 8.314 divided by 298. And we get Kp to be 1.4 times 10 to the negative 6. Awesome. we've done it. And so that would be the equilibrium constant at this temperature. If we look at Q, we can see Q is going to be greater than K in this case. So our reaction is going to probably go to produce more reactants, right? So we're going to be working with that. Alrighty. Exciting stuff. Let's see, what else do we want to do here? Any other questions that are sticking out that we'd like to do? Let's see. Let's see here. We've done those. Let's look at this page. I feel like we've kind of gone through pretty much most of the similar type of calculations that we'll have here. It's the same thing. Alright, well, I think we've done a good amount of kind of just problems today. I have to think if I want to start electrochemistry tomorrow or just start it after spring break. So I'll make that determination. Maybe we'll just take a day off. So we'll see. Because we're a little bit ahead of schedule here. Which is fine. So, cool. Any questions on any of these that we've done? Or we still have time to do another one if any of them kind of jump out at you as being ones you'd like to go over. Okay, well, in that case, I'll let you know on Discord if we'll meet tomorrow. I'll make my decision. Maybe we'll just take the day off and have an early spring break. Who knows? So we'll see. No spring break for honors people, though. We're still on for Thursday, so we'll continue on. So cool. Alrighty. Well, with that, I guess we're good. I will potentially see you tomorrow or potentially see you after spring break. So if I don't see you tomorrow, have a good spring break. Obviously, there will be no class next week as a result. So cool. Awesome.